Okay. So welcome everyone again. So this is the beginning of chapter 12. As you know that in chapter 11 we talk about the transformation, the solid transformation or liquid transformation at a specific temperature. So if you cool down from a certain temperature to another temperature, okay, you're going to have some phase transformation, right? But we did not talk about how long it's going to take in order to finalize the final product, okay? And if there is a transformation, sometimes this transformation is going to require that atom diffuse from one point to another. Let's give a look at this diagram here. I think that most of you right now are familiar with this diagram. So this is the iron-iron carbide phase diagram, okay? If you remember, in the y-axis, we have the temperature. In the x-axis, we have the carbon concentration. I said that 6.7, you have the intermetallic compound. Wonderful. Okay. So now, if you remember, we said that at 0.76, what we have at 0.76, we have the Eutectoid reaction that's going to happen, right? Well, the Eutectoid reaction going to happen anywhere in this temperature, 727. But at this specific composition, 0.76, gamma austenite going to directly transform to two types of solid, which is alpha plus iron carbide. So that means if you cool below Eutectoid temperature, it was 727, what's going to happen? Gamma austenite is going to transform to alpha plus iron carbide. This is the reaction. Okay, wonderful. The question that we have right now, at this point, you see this, at this point, where is the E? You see Eutectoid at point E, here. What is the composition of the alloy? So the composition of the alloy is 0.76. So 0.76 carbon, and the remaining is iron. But you have to notice something. When you cool down below the Eutectoid temperature, right? Now you see that the carbon will be divided into two groups, right? One group, they're gonna go and form, or are gonna be part of the alpha, and the other group of the carbon will go and form what? Iron carbide, right? Right? So that means there will be some diffusion, right, of the carbon atoms in this transformation. And we know that there is solubility limit for alpha, right? So alpha can accommodate very small amount of carbon, which is around 0.022. However, iron carbide can accommodate more carbon. So what's going to happen if you look at this diagram here, that you see this is gamma austenite, right? And gamma austenite start to transform to pearlite, اللي هو عبارة عن alpha iron carbide, alpha iron carbide, alpha iron carbide. So we have a lamellar structure, layer by layer, تمام? And you see that this is the gamma, and this pearlite, it will consume the whole gamma austenite at the end of this process. Similar to the water to ice, in the beginning, the ice crystals start to nucleate in the water, and then it starts to grow until the ice crystals will consume the whole water, the whole liquid. Similarly, هنا, pearlite will grow until it consumes the whole gamma phase. لاحظ what's happening here, إنه الcarbon will diffuse, right? Some of them will be part of the alpha, but most of them, they're going to diffuse to go to the iron carbide phase. لاحظ. So here you see the carbon is diffusing, right? So diffusion, معناته it's time dependent. معناته diffusion of atoms, in order for atoms to move from one point to another, that movement requires time, right? And I would like to ask you a question. Try to think about it for 10 seconds. You think if we take a material from high temperature, let's say if we take it from, okay, if we take it from this point here, and we take it to this point, which is around 700 Celsius, around 700 Celsius, or we take it to around 600 Celsius. Which one you think the carbon can diffuse to a longer distance? If we take it to 700 Celsius, or we cool it down to 600 Celsius, does it matter or does it matter? Does it matter or does not matter? Well, the answer is it matters. Why? Because if you cool down to much lower temperature, you are kind of more freezing the atom. So the atom does not have energy to diffuse to longer distance. However, if you cool down to a little bit higher temperature, the atoms still, they are energized, so they can move to longer distance to their preferred position. What I mean by that? Let's get back to this slide again. So we say that carbon will diffuse to the iron carbide layer, right? Because iron carbide can accommodate more carbon. Wonderful. Now, if you cool down to a higher temperature, the canal eutectoid temperature 727, if you cool down just below the eutectoid temperature, now you are cooling down still to higher temperature. Now to those carbons that you see here, they're still energized, عندهم energy. طيب بالتالي they can diffuse longer distance to go to the preferred position and preferred locations, right? معناته the carbon can diffuse more into the iron carbide. However, if you cool down to much cooler temperature, يعني if you cool down, let's say from above 727 إلى let's say to 600, إيش اللي حيصير عندنا? What's going to happen? Now you're not giving the carbon enough energy to diffuse. بالتالي they're going to transform very quickly to the final product. طيب وبالتالي that will impact how again impact the thickness of the layers that you have. Okay, wonderful. Similarly, يعني if you have similarly if you have, I don't know if you have tried ice cream that's made by liquid nitrogen, well, ice cream that's made, they solidify in the fridge. In the fridge you have around -15 Celsius, right? And liquid nitrogen, the temperature is around -196 Celsius. I don't know if you have tried before the difference between ice cream that's made from the fridge and the ice cream that's made by using liquid nitrogen. You're going to find big difference between the two. The difference in the ice crystal size, right? So some of them will dissolve completely in your mouth. Some of them are going to take time, okay? The one by liquid nitrogen, because you do a quick solidification, right? What's going to happen? Usually going to end up having small ice crystals, and all the regions will all of a sudden going to transform to small ice crystals. However, if you place in the fridge, right? So -15 Celsius is not that cold compared with -196. What's going to happen? Ice crystals will start to form, and then they start to grow, and they're going to grow larger. So next time you try to see the difference between liquid nitrogen ice cream and regular ice cream. Okay, wonderful. So the point here, if you look at this figure over here, is very informative figure, because it's going to tell you when the nucleation of the new phase will start and when it's going to end, according to the temperature that you're cooling to. طيب? So you know that if you cool down from 727 eutectoid temperature to 675, الدلتا T حقتنا small, right? You have smaller delta T. Do you agree with me? So you have smaller delta T, 675. Now, if you cool to, this is 675, this is so when you cool to 675, لاحظ هنا في الإكس axis عندك how much time it needs in order to start the nucleation. فلاحظ هنا it needs more time in order to start the nucleation حق a new phase. If you cool down to lower temperature, 650, you need smaller time in order to start the nucleation. If you cool down to much lower temperature, larger delta T, right? You notice that, and no, what do you have? You need smaller time in order to start the nucleation. Okay, but what is the y-axis? Y-axis is telling you this is 0% pearlite formed. This is 50% of the pearlite already formed, and this is 100%. ممتاز. So معناته this figure is telling you when the nucleation gonna start at this temperature and when it's completely formed خلاص transformed عندك من gamma austenite إلى pearlite. Okay, for example, let's take an example. Let's take 600 Celsius, or let's take 675, right? So the nucleation gonna start around, let's say 20 Celsius, 20 seconds. تمام؟ يعني إيش؟ يعني if you cool down from this point, the red point, to 675, طيب, to 675, إيش اللي يصير؟ Nothing gonna happen in the first 20 seconds. After 20 seconds, the nucleation starts to happen. طيب. So after nucleation gonna start to happen, and then after 100 seconds, 50% of the gamma austenite gonna transform to pearlite. تمام؟ بعدين, and then you need around maybe 600 seconds in order to fully transform gamma austenite to pearlite. Okay, great. معناته انه at a specific temperature we need time in order to start the nucleation, in order to fully transform the whatever you have to the new phase. Be careful that if you cool down to lower temperature, you can notice that this can happen in a quick manner, because at 600 Celsius, you see that the nucleation gonna start around 2 seconds. After 2 seconds at this temperature, then it's gonna need only around maybe 7 seconds in order to fully transform gamma austenite to pearlite. So depending on the temperature, right? The transformation period gonna be different. Here, if you have smaller delta T, what's gonna happen? Well, you need around 600 seconds. If you have larger delta T, well, you need only 7 seconds, and everything gonna happen, right? Well, someone would say, okay, let's do the 600 Celsius. Right? It's much better because you can get a quick transformation. We're gonna say, yes, you're gonna get quick transformation, but there's a problem there, right? The problem is, depending on the temperature, we say that the atoms will have different amount of energy. If you cool it to higher temperature, the atoms more energized, so they're gonna form layers. And if the atoms at 600 Celsius not energized, they're gonna form layers. There will be difference between these two layers, right? There will be difference between these two layers. Let's look how these two layers gonna look like. Two different layers gonna look like at higher temperature, lower temperature. Okay. Now, if you cool down to higher temperature, you're gonna get coarse pearlite. You see, you're gonna get thick layers. Why are you gonna get thick layers? Because the carbon is energized. They can diffuse to longer distance to form the iron carbide phase. However, if you cool to much lower temperature, what's gonna happen? Those carbons, they don't have enough energy. They're gonna have short distance diffusion. What is the result of that? Well, the result of that, they will end up having thin layers of pearlite. As we can see, it's called fine pearlite. So again, if you cool down to higher temperature, you're gonna get coarse pearlite. If you're gonna cool down to cooler temperature, lower temperature, you're gonna get fine pearlite. Okay, doesn't matter. It doesn't matter. The mechanical properties of these two are going to be different. What is the difference? Well, the difference is we said earlier, iron carbide is a brittle, right? We said iron carbide is brittle, is hard and brittle. And we say that alpha ferrite is ductile, right? So that means if you have thick layer of alpha, as you can see here, thick layer of alpha, if you have thick layer of alpha, that means you have more ductile phase in this region compared with the fine pearlite, right? So you expect a coarse pearlite to be relatively soft, right? However, the fine pearlite, you have thin layer of alpha, وبالتالي you expect إنه to have more, it's relatively hard compared with the coarse pearlite. Great. Okay, so now the previous slide is trying to say that cooling down to a specific temperature is not the end of the story. Well, we have to dig deeper and to see how much time it's going to take at that temperature. So if we cool down to a specific temperature, we need to look how much time it's going to take for the transformation to start and to end. So chapter 12 is about correlating between temperature and time, between temperature and time. Okay, great. And at the end of the day, it matters because it's going to change the mechanical properties of the material. Okay, that means at specific temperature, we want to have 3 points. The start, when the nucleation going to start. The middle of the transformation, we have 50% already transformed. And the last point is the end of the transformation, right? So at each temperature, we need 3 points. But I would like to ask a question, and I would like you to think for, let's say, 5 seconds. Okay. You think if we cool down to much lower temperature, do you think the nucleation will start faster or slower? Think about it. If you cool down to lower temperature, do you think the nucleation will start at faster or slower? If you cool down to much colder temperature, do you think the nucleation is going to start faster or slower? Think about it. Okay. The nucleation will start faster, right? Why? Because we talk about, we are not giving time to the carbon to diffuse. بالتالي خلاص, the transformation is going to happen faster, but that will have its own impact on the mechanical properties. طيب. Okay, then معناته for a specific temperature we have 3 points. We have start, middle, end of the transformation. At each temperature we have start, middle, and then end of the transformation. Hello. Now let me show you a figure that that has these 3 points for each temperature. طيب. Let's give a look here. Okay. خلينا نطالع في هذه. Okay, so let's give it a look here. Now, let's take 675 Celsius. We say that in transformation, he would not start before around 60 seconds or 70 seconds, right? So we need 70 seconds in order to nucleation to start at this temperature. 675. And then you need around 100 seconds in order for 50% of the austenite to transform to pearlite. And then you need around 600 seconds in order to have full transformation. So these are 3 points. Okay, wonderful. So this point, and we're going to establish what's called TT diagram. TT diagram اللي هو يسمى time temperature transformation. You're going to correlate temperature with time. Temperature with time. Temperature with time. Hello? So at 675 temperature, 675, we said this is going to be the beginning of the nucleation. So this point corresponding to this point here, this is the beginning of nucleation. The dashed line اللي هنا is telling you 50% of the transformation. يعني we need this amount of time in order to have 50% of transformation. We said we need 3 points, صح? 3 points. Start, middle, and then final, right? And then we need this amount of time in order to have full transformation of gamma austenite to pearlite. حلو؟ معناته انه هنا at this temperature we have gamma austenite, right? Gamma austenite is going to transform to pearlite at the end, but it needs some time, right? And this figure is going to tell you how much time it needs, right? So here it's going to need, so if we hit the green curve, it's telling you that, well, now we have the gamma austenite start to transform to pearlite. 0% now we have pearlite, right? And then at this point you have 50% pearlite, يعني 50% pearlite, 50% gamma austenite, باقي ما تحولت. طيب. And then if we hit the red curve, now we have 100% of the gamma austenite transform to gamma austenite. عفوا, transform to pearlite. Great. Okay, then what's going to happen if you go to lower temperature? Imagine if you cool down to lower temperature. Let's say you cool down to 600 Celsius. You see, we say that if you cool down to lower temperature, nucleation will start faster. Right? So nucleation will start faster. So if you cool down to lower temperature, nucleation gonna start faster. معناته nucleation here, you see that at this temperature now you're gonna hit the green curve much earlier compared to the 675, right? So you have the curve here, right? So this is the beginning of the transformation to gamma austenite, and then once you have the dashed line, 50% of whatever you have already transformed to pearlite. Now if you hit the red curve, all what you have, all the raw material that is not stable, اللي هو الجاما austenite, transformed to pearlite. Just I would like to bring to your attention that gamma austenite is not stable under the Eutectoid temperature اللي هو 727. So if you cool down below 727, gamma austenite is willing to transform to something else because it's not stable. طيب. However, pearlite, the gamma austenite transform to pearlite is a stable phase. معناته even if you cool down then to room temperature, nothing gonna happen because pearlite is stable. Pearlite is stable. Nothing gonna happen to it. It's happy with itself. طيب. ممتاز. إذا هذا الفكرة من chapter 11. The idea of chapter 11, we would like to introduce to you the time temperature transformation diagram, TTT diagram. Okay. And that diagram, you're going to know when the transformation gonna be initiated, and then when 50% of that transformation will happen, and then when the 100% of transformation, the complete transformation will happen, how much time you need. Okay, great. Wonderful. And what we said that so this is the other part. This is what's going to happen if you cool to much lower temperature. In this diagram we said what's going to happen up to 500 Celsius. Well, up to around 500 Celsius you're going to get something called pearlite, and we know from the beginning of this lecture we say that and we have two types of pearlite. We have coarse pearlite and you have fine pearlite. When we're going to get coarse pearlite? Well, you're going to get coarse pearlite if you cool to little bit higher temperature, right? If you cool down to lower temperature, what's going to happen? You're going to get fine pearlite. But what's going to happen if you cool down below 500? Well, you're going to form something completely different. It's called bainite. And this is going to be the topic of next lecture, inshallah ta'ala. Okay, let's give a look into this. Now, you cool down from gamma austenite to 675. We said that gamma austenite is not stable. معناته إنه if you cool down that temperature and you keep it at that temperature, right? This transformation will happen, but it will not happen all of a sudden. You need some time, right? So that once you hit the red curve, the green curve, gamma austenite still 100% you have gamma austenite. Once you hit the green curve, the gamma austenite start to transform to pearlite. If you hit the dash line, 50% of gamma austenite transform to pearlite. And once you hit the red curve, the whole gamma austenite transform to pearlite. But it depends on which temperature you cool to. We said that we can have something called coarse pearlite. You can have thick layers, and you have something called fine pearlite. You have thin layer of thin layer of pearlite. Okay. Now let's say, suppose that a steel of Eutectoid composition is cooled to 550 from 760. يعني cool down. You go like, suppose that you cool down at Eutectoid composition يعني at 0.76. يعني here we are fixing the composition. عشان عندنا هنا, because in the y-axis you have the temperature, in the x-axis you have the time, the duration. What's going to happen if you fix the time? Well, what's going to happen that if you fix the time, if you fix the composition and you cool down to this temperature, right? And then he said, and you cool down, what's going to happen? How long it will take for the austenite-to-pearlite reaction to go to 50% completion? And how much time at this temperature, 550, we need in order to have 50% completion? Well, if you're gonna go head the dash line, you go down, you need 2.5 seconds. But how much time I need in order to have 100% completion of this step? Well, you're gonna continue until the head and you hit the red curve. That means you need around 6 seconds. So you need 6 seconds in order to have full transformation of gamma austenite to fine pearlite. Okay, wonderful. So I'm gonna stop here. Inshallah, next class we're gonna continue the discussion about the time temperature transformation diagram.